Before July 1st, 2025, we thought we understood interstellar visitors. Clear models, powerful telescopes, everything was under our control. Then 3IATLAS appeared, and suddenly everything we knew was turned upside down. It was producing carbon dioxide at rates we had never seen before. This was impossible for us. Its gas clouds extend farther than Earth's orbit. Its chemistry defies all the formation theories we have, and the more we observe, the stranger it gets. But here's the real shock. What if this is not just a comet, and at that very moment, all our knowledge is turned upside down. All the technologies we possess in the world are defeated by a rock barely the size of a city. What would you do? Click to subscribe and discover the mysteries of 3IATLAS. Could this be a discovery that lasts a lifetime, or proof that the universe still holds secrets we're not ready to understand? If you're ready, let's begin. One of the greatest mysteries of the universe sometimes reveals itself in the most ordinary moments. On July 1st, 2025, at the Atlas Telescope Station in Chile, such a discovery took place. Like every discovery, it happened in an unexpected time frame. Recorded at 1437 Universal Time, this moment will remain as a turning point in the history of astronomy. This discovery was one that would make humanity question its loneliness in the universe. Maybe it would even be evidence that there are other civilizations out there. Perhaps it could be the first step toward contact with another intelligent species. And what was this discovery? Keep watching, you will learn with time. The interstellar object known as 3IATLAS appeared only as a faint smudge located 4.5 astronomical units away from the Sun. But the first orbit calculations revealed a shocking truth that sent waves through the astronomical community. This visitor was moving on a hyperbolic trajectory. Like an arrow released from a bow, where was 3IATLAS heading? To none other than the galaxy humanity lives in. Of course, every galaxy is unique, but let's put those details aside. Officially catalogued as C2025N1 this comet carried a much deeper meaning. It was the third confirmed interstellar object, and each new observation proved how extraordinary it really was. Don't think of its discovery as just a discovery. The arrival of 3IATLAS was like a cosmic message from the universe itself, mysterious and hard to read. Even its speed was astonishing. 209,000 kilometers per hour. This made it the fastest solar system visitor ever recorded. To put that into perspective, take the speed of a regular bullet and multiply it by 170. Imagine Sonic crossing from one city to another in just seconds. Incredible, right? For those who don't know Sonic, think of him as an extremely fast blue hedgehog. But 3IATLAS defied expectations not only with its speed, but also with its chemistry. When the Gemini North Telescope in Hawaii captured the first detailed images, astronomers found an active coma, a cloud of dust and gas, surrounding this alien comet. This was not a dead rock from the cold interstellar void. It was alive, breathing. Like a mystical beast that had slept for centuries in the depths of space, it now seemed ready to reveal itself to humanity. And then came the James Webb Space Telescope's spectral analysis, unveiling something unbelievable. Unlike normal comets, 3IATLAS was producing carbon dioxide at a ratio of 8.1 compared to water. This ratio was so extreme that it shocked the scientific world. It was as if this object carried the atmosphere of a frozen planet with it. SphereX data brought even more surprises. The carbon dioxide cloud stretched nearly 4 times the Earth-Moon distance, 348,000 kilometers. A gas giant made of CO2, yet orbiting like a comet. And despite its mass, its orbit showed astonishingly little deviation, almost impossible under known physics. The discovery shook science like an earthquake. How could such a small nucleus generate such a massive cloud? Physics said it couldn't, but Atlas was doing it anyway. This triggered one of the most unprecedented global collaborations in astronomy. NASA, ESA, and observatories worldwide united to learn every possible detail about this interstellar visitor. Hubble captured the sharpest images, JWST analyzed its chemical secrets in infrared, Swift tracked ultraviolet radiation, and SphereX mapped the vast carbon dioxide cloud. Humanity was collectively trying to understand this alien object. Yet, Atlas kept its secrets. Its orbit followed the paths of solar system planets with surgical precision. On October 29, 2025, it would make its closest approach to the Sun, but Earth would be on the opposite side. Between late September and early November, Atlas would vanish into the Sun's glare, invisible to all telescopes. This shrinking observation window worried scientists. By December, when it reappeared, Atlas would be speeding away at over 240,000 kilometers per hour, fading night by night. Time was against us. Each minute mattered. Before Atlas vanished forever, we had to uncover its hidden treasures because Atlas did not behave like any comet we knew. Its emissions, its orbit, its chemistry, they all broke the rules. The discovery of C-2025N1 Atlas sparked one of the greatest scientific mobilizations in history. Every continent, every space agency, every observatory working together, driven by a cosmic curiosity deep within humanity. But the question remains: how did an object like Atlas manage to stir humanity's wonder on such a vast scale? And more importantly, before it disappears into eternity, can we uncover its secrets? The journey and timeline of the solar system. The solar system works like a giant clockwork mechanism. Planetary orbits trace predictable paths, and gravitational forces have been performing the same dance for billions of years. Now, within this cosmic machine, 3IATLAS, fired from another galaxy like a bullet, races forward at an incredible speed. Or Atlas seemed to slot itself perfectly into the clockwork, finding its place as if by its own will. But how did it navigate? In a foreign system, how could it move along a precise orbit? Did it have a mind? No, it had none. It was a miracle. Our universe is full of such miracles, yet we often fail to notice them. Everything exists in a delicate balance. If Earth's axial tilt were 10 or 40 degrees instead of 23, humanity could not survive. The universe is full of these wonders, and because we are used to them, we don't even notice. And none of this is coincidental. Who do we thank for these blessings? The trajectory of the interstellar object Atlas within the solar system reads like a carefully planned tour program. Yet this program was written long before Earth existed. Its closest approach to the Sun, the perihelion, will occur on October 29, 2025, and it won't be a casual distance between the orbits of Earth and Mars, about 130 million miles away. It will pass blazing by. The harshest part of this cosmic choreography is revealed here. While 3IATLAS swings past the Sun, Earth will be on the exact opposite side. This coincidence is pure torture for astronomers. The inability to observe Atlas while it performs its spectacle, with all other planets seemingly invited except Earth, is agonizing. Why was Earth left out? The observation window presents the very definition of astronomical frustration. Scientists have about 3 months to gather data before it disappears behind the Sun, followed by a 6-week wait until it becomes visible again in December. For an interstellar comet, this timeline represents the last chance to study a body that will never return. Yet its orbit offers fascinating opportunities from different perspectives. On October 3, 2025, 3IATLAS will pass just 29 million kilometers from Mars, closer than some of the planet's own moons. The robotic fleet orbiting Mars, especially the Mars Reconnaissance Orbiter, with its powerful high-rise camera, may witness a historic encounter with this alien comet. In astronomy, geometry is everything, and this geometry is both a gift and a curse. When Atlas reappears in early December, it will be visible in the pre-dawn sky within the Virgo constellation, gradually climbing toward Leo in the following weeks. By then, it will already be speeding away from the Sun at over 240,000 kilometers per hour. Humanity will chase it, yet it will always be ahead. A cosmic game of tag. Why does it flee? No matter how far it goes, we will continue to track it. It's like a loop, the pursued and the pursuer. But what is this chase for? For amateur astronomers, the news is less exciting. Even at its brightest, Atlas will only reach magnitude 11 to 12, visible only through telescopes as a faint, blurry dot among millions of stars. Its orbital mechanics reveal more than just speed. They show a wrong motion. Its hyperbolic orbit indicates an initial velocity of about 25 kilometers, enough not only to escape the solar system, but even to evade the gravitational embrace of our galactic neighborhood. See 2025 N1 Atlas is not recently ejected debris. This object has been wandering the galaxy for an extremely long time, perhaps millions or even billions of years. It traveled the depths of space long before humanity existed, even during the age of dinosaurs and even before Earth itself was formed. In spring 2026, 3IATLAS will make another important passage, this time near Jupiter in March. This distant encounter has prompted NASA to propose a course adjustment for the Juno spacecraft orbiting the gas giant. This daring idea could transform a mission designed to study Jupiter's internal structure into humanity's first close encounter with a confirmed interstellar visitor. Timing is critical. Missing the window by hours would make the maneuver impossible. Perhaps the most humbling aspect of Atlas's journey within the solar system is the cosmic perspective it provides. With billions of dollars in instruments, coordination across multiple space agencies, and the best minds in planetary science mobilized, we are studying a body that will remain close to us for less than 2 years. The trajectory of 3IATLAS within it. The solar system is more than just an orbit. It is a timeline of opportunities and constraints, windows opening and closing according to the ancient laws of orbital mechanics. With each passing day, we come a little closer to our last chance to unravel the mystery of this traveler from the stars. Atlas's orbit itself was a map. Its closest approach to the Sun would occur on October 29, 2025, but at that critical moment, Earth would be on the exact opposite side. This caused astronomers the greatest frustration. They would miss the most important moment, the period when Atlas was nearest the Sun and at peak activity would be completely unobservable. The global observation campaign mobilized after the discovery of 3IATLAS was perhaps the most comprehensive international collaboration in the history of astronomy. NASA, ESA, and observatories around the world joined forces to collect every possible piece of data about this interstellar visitor. While the Hubble Space Telescope provided the highest resolution images, the James Webb Space Telescope detailed its chemical composition through infrared spectroscopy. The Swift Observatory tracked ultraviolet emissions, and SphereX's wide-field camera mapped the massive carbon dioxide cloud. Yet 3IATLAS maintained its defiance from the moment it was discovered. Every new observation brought more questions. The story of this visitor was more than an astronomical discovery. It was proof that the universe still holds secrets we have yet to solve. Atlas's chemical signature did not match any environment known to us. This suggested it may have formed in another star system, perhaps under conditions billions of years older than Earth. The narrowing observation window reminded scientists that every moment was precious. Its time within the boundaries of the solar system was, by cosmic standards, the blink of an eye. Atlas would leave as it came at the same incredible speed, this time forever. The route across our solar system, imagine the solar system as a massive clockwork mechanism, each gear a performance troupe, each tick-tock the sound and rhythm of the show. Now think about how these performances unfold. It's awe-inspiring, isn't it? Planetary orbits trace predictable paths through space and time. Now imagine a bullet fired from another galaxy passing through this cosmic machine at impossible speeds, slipping through the gears with mathematical precision. This bullet is 3IATLAS, and its trajectory through our solar system resembles a carefully planned tour of the inner system. Yet this journey was charted in the stars billions of years before Earth even existed. C2025 N1 Atlas will reach its perihelion, closest approach to the Sun, on October 29, 2025. This is no leisurely distance for most comets. Instead, it will blaze between the orbits of Earth and Mars, approximately 130 million miles from our star. As 3IATLAS makes its closest pass, the scientific community will be dreaming of observing it. Yet, frustratingly, this elusive object will constantly remain outside our observation windows. 3IATLAS will be positioned directly opposite the Sun from Earth. From late September to early November, our visitor will vanish in the Sun's glare, invisible to every telescope on Earth or in orbit. It's as if the universe conspired to hide the most critical moments of this interstellar encounter. This observation window tells a story of astronomical disappointment. Scientists have only about 3 months to collect data before Atlas disappears behind the Sun. Then, when it reappears, possibly in December, there will be just 6 more weeks before the object becomes too faint and distant for meaningful study. For any researcher, this is a nerve-wracking deadline, but they are studying something that will never return. Yet the orbit offers fascinating opportunities for those willing to think beyond Earth's perspective. On October 3, 2025, 3IATLAS will pass just 29 million kilometers from Mars, a distance so close that even Mars moons don't approach it. This is a golden opportunity for the scientific community, a chance to capture an alien comet from a Martian vantage point. Robotic explorers orbiting the red planet, including the powerful high-rise camera, may photograph this visitor like never before. In astronomy, geometry is everything, and this geometry is both a gift and a curse. When 3IATLAS reappears in Earth's sky in early December, it will grace the pre-dawn hours in Virgo and climb toward Leo in the weeks that follow. By then, however, it will be moving away from the Sun at over 150,000 mph, fading every night as it returns to the cosmic depths. For amateur astronomers hoping to see this interstellar object, the news is less promising. Even at its brightest, 3IATLAS will only reach magnitude 11 or 12, visible only through telescopes, appearing as a faint, blurry speck among millions of stars. There will be no naked eye display, no bright tail stretching across the sky like Hale-Bopp or Neowise. Our visitor seems to choose humility over spectacle. Though the scientific community may wish otherwise, deviation from its orbit could spell disaster for our solar system. Orbital mechanics reveal yet another layer of mystery. 3IATLAS is not only moving fast, it is moving wrong. Its hyperbolic trajectory suggests an origin velocity of about 25 kilometers relative to the local standard of rest, fast enough to escape not only our solar system, but potentially the gravitational embrace of our entire galactic neighborhood. In the spring of 2026, 3IATLAS will make another significant pass, and we wait with bated breath, unsure of what to expect. This time, it will pass near Jupiter in March. This distant encounter has already sparked proposals to redirect NASA's Juno spacecraft orbiting the gas giant for a daring close encounter. This bold idea requires precise orbital mechanics and perfect timing. A mission designed to study Jupiter's interior could become humanity's first close encounter with a confirmed interstellar object. The risks are high, but so are the potential rewards. If successful, this mission could become one of the most celebrated discoveries in history. Perhaps the most humble aspect of this celestial program is the cosmic perspective it reveals. Here we are, tracking an object with billions of dollars worth of instruments, coordinating observations across multiple space agencies, and mobilizing the best minds in planetary science, all to study something that will remain near us for less than 2 years before vanishing forever into the galactic night. The path of 3IATLAS across the solar system is not just an orbit. It is a timeline of opportunities and constraints, opening and closing according to the ancient laws of orbital mechanics. And with each passing day, we get closer to our last chance to unravel the mystery of this traveler from the stars. Now, ask yourself, within such a brief window of encounter, will scientists be able to uncover all the secrets of this alien comet? Are we alone in the universe, or are there other civilizations beyond humanity? And if we are not alone, could we be among the most advanced civilizations? The outcome of this cosmic race is a test, not only of our advanced instruments like the James Webb Space Telescope, but also of our determination to understand the deepest secrets of the universe. First observations: what Hubble saw. On July 20th, 2025, when the Hubble Space Telescope turned its lens toward 3IATLAS, the universe presented us with a paradox wrapped in starlight. The images captured by Hubble's digital sensors were at once familiar and entirely alien, a softly glowing cloud of dust and gas against the endless darkness, arranged in a geometry that no textbook could have prepared us for. The technical details of 3IATLAS, the interstellar object, read like poetry, written in the language of physics. The comet's solid heart, the nucleus, appeared as a bright point source embedded within its atmospheric envelope. What could the scientific community hope to find in that point of light? What secrets did it hold? Even though scientists did not, yet, have the answers to these questions, rest assured, they were working to solve them. Hubble's flawless optics allowed researchers to place an upper limit on its size, no more than 5.6 kilometers in diameter. To put this in perspective, it was smaller than many cities on Earth. Yet this small piece of an alien comet produced a coma that extended thousands of miles in all directions. Familiarity became strange here. Hubble tracked C2025N1 Atlas against the background stars, keeping it at the center of its field of view. As a result, the stars themselves appeared as bright streaks across the image, creating a spiritual backdrop that made it seem as if the comet were flying through a tunnel of light. This photographic technique transformed scientific documentation into accidental art, revealing the relative motion that separated this visitor from everything else in our cosmic neighborhood. The coma itself told a story of thermodynamics played out on the interstellar stage within our solar system. As 3IATLAS approached the Sun, crossing the 4 astronomical unit threshold, where water ice begins to sublimate seriously, its nucleus likely began releasing material that had been dormant for millions of years. Dust particles, freed from the icy matrix, formed a roughly spherical cloud around the nucleus, yet with a pronounced elongation pointing away from the Sun. This was not random. Physics sculpted the coma into the characteristic teardrop shape, as confirmed by observations from the James Webb Space Telescope under the combined influence of solar radiation pressure and gravitational forces. Something about 3IATLAS's tail was unusual. In most interstellar comets, the antisolar tail, material pushed away from the Sun by radiation pressure, is prominent and easily visible. In 3IATLAS, this feature was astonishingly subtle, almost hidden. Initial Hubble analyses suggested its presence but could not confirm it with certainty. The geometry seemed wrong, as if we were viewing the tail from an angle that compressed it into invisibility. The mysterious tail of 3IATLAS was magnificent. Some celestial bodies like this in space exhibit such subtle features, a testament that humanity is not left to the universe entirely on its own, and proof that the cosmos did not form randomly. Even human bodies can be considered miracles in themselves. At the end of August, when the Gemini South Telescope in Chile captured deep images and finally revealed what Hubble had only hinted at, the ambiguity persisted. There it was, a faint but definite anti-solar tail, stretching like silky threads into the solar wind. Hubble's measurements showed that 3IATLAS was shedding material, at rates comparable to solar system comets, observed at similar distances from the Sun. This might have seemed reassuring, a proof of normal, predictable behavior. Yet one critical detail remained. This object had spent eons in interstellar space, exposed to cosmic radiation that should have fundamentally altered its surface chemistry. Although Hubble's observations provided the highest resolution possible from Earth orbit, allowing scientists to constrain the nucleus size and map the coma's morphology, they could not resolve any surface features or rotation. The nucleus remained a point source, its secrets locked behind the glowing veil of its own atmospheric emissions. We were observing this visitor through the mist created by its own light. Hubble's observations of 3IATLAS revealed that this interstellar object was not an ordinary piece of debris. It demanded explanation, challenged assumptions, and tested our understanding. See 2025 N1 Atlas, continuing its journey through the gentle darkness of space, was now illuminated by our Sun and scrutinized by humanity's most advanced instruments. Despite all our technological power, the visitor remained essentially unknown, a mystery wrapped in starlight, shrouded in its own luminous breath. Hubble's first observations provided a visual foundation, a reminder that the universe is still full of secrets capable of astonishing us. Though this foundation was solid, the question remained: would the new data built upon it be equally reliable? Still unknown. The unsolved mysteries. 3 months after the discovery, with the world's most advanced instruments focused on 3IATLAS, we find ourselves in a situation of knowing very little about very much. Every observation revealed new aspects of this interstellar object. Yet the most fundamental questions remain unanswered. This uncertainty leaves the scientific community helpless. So, when can this uncertainty turn into something definite? The uncertainty in the fundamental questions of 3IATLAS also prevents scientists from making plans for the future. The nucleus size dilemma perfectly exemplifies our predicament. Hubble's imaging limits it to somewhere between 320 meters and 5.6 kilometers in diameter, a very wide range covering everything from a large building to a small city. This is not a failure of the instruments. It is the inevitable consequence of studying an unresolved object cloaked in its own luminous atmosphere. The 3IATLAS nucleus could be a compact, bright sphere or a long, dark mass tumbling through space. Without direct resolution, we are essentially guessing. The rotation state remains equally mysterious. Most small objects in the solar system rotate with periods measurable in hours, creating detectable brightness variations as they tumble through changing cross-sections. Why is 3IATLAS breaking the rules like a criminal? If these rules could be broken casually, humans could fly defying gravity without any instruments. How did 3IATLAS manage to break the laws? Yet, see 2025 N1 Atlas, proved to be frustratingly stable in visible brightness, showing none of the periodic variations that would reveal its rotation speed or orientation. The question of water has become something approaching a scientific drama. Early observations with the Swift Observatory's ultraviolet and optical telescopes detected hydroxyl radicals, a reliable indicator of water vapor typically broken down by solar ultraviolet radiation. This discovery, though not particularly promising, will open the door to other discoveries, so we must never lose hope. The presence of OH suggested a significant water gas outflow consistent with comet expectations. However, SphereX's subsequent mapping found a surprisingly weak water signal, contradicting Swift's detections. Tail morphology adds another layer of uncertainty. At the end of August, Gemini South's detection of the antisolar tail finally confirmed what theory demanded: material pushed away from the Sun by radiation pressure. But why did it take months to clearly identify this feature? Compared to typical interstellar comets, the tail's thinness suggests either unusually large dust particles resistant to radiation pressure or a viewing geometry that compresses the tail nearly into invisibility. Activity patterns may present the most intriguing unknowns. Hubble images show material flowing toward the Sun, extending the coma sunward instead of away from our star. This true reversal, seems to have subjected the scientific community to a storm of questions. This counterintuitive geometry could, of course, be an optical illusion, and the idea of it being an illusion sounds reasonable. This non-intuitive geometry initially puzzled observers until they realized that perspective in three-dimensional gas flows can create optical illusions. Composition mysteries extend beyond CO dominance. While the James Webb Space Telescope and SphereX mapped the main gas species, they barely traced the surface of trace chemicals. What organic compounds are present? Sulfur-bearing species? Noble gases? Each trace component can provide clues about formation, temperature, radiation exposure, and the chemical environment of the parent planetary system. Perhaps most frustrating of all is our inability to study 3IATLAS's behavior around perihelion, exactly when solar heating should drive the most dramatic changes in activity and composition. Missing the comet at its best dance is painfully frustrating. People get upset when they miss some opportunities in evaluation, but they wouldn't have been able to seize the opportunity anyway. It's like a contestant losing in a show designed for people to earn money and not getting the prize, even though the money wasn't theirs to begin with. Therefore, humanity should not be upset that we missed seeing 3IATLAS, and we should strive to conduct stronger studies. What is interstellar? The cosmic passport criteria. The cosmos does not issue passports, but if it did, 3IATLAS would carry an identity document from another star system. Understanding a truly interstellar object requires diving into the mathematics of orbital mechanics, a language in which eccentricity values and hyperbolic orbits tell cosmic travel stories spanning millions of years. In the precise terminology of celestial mechanics, any object with an eccentricity greater than 1 is independent of our solar system. It follows what mathematicians call a hyperbolic orbit, a path that opens to infinity instead of closing into an ellipse. IATLAS has an eccentricity of approximately 1.7. This not only means it is independent, but also that it moves fast enough that even Jupiter's massive gravitational influence could barely deflect its trajectory. However, eccentricity alone does not complete the story. The truly diagnostic measurement is something called V infinity, the speed an object would have relative to the Sun if it were at an infinite distance beyond the reach of the Sun's gravity. For objects born in the solar system, this speed is essentially zero. They are gravitationally bound, and even if completing their orbits takes millions of years, they will eventually return. See 2025, N1 has a V infinity of roughly 25 km/s, unmistakably confirming that it was born elsewhere. To appreciate this speed, consider that Earth orbits the Sun at about 30 km. 3IATLAS moves through the solar system at almost the same speed at which our entire planet orbits our star. The discovery process reveals just how rare these interstellar visitors truly are. The ATLAS survey system consists of 4 robotic telescopes designed to hunt potentially hazardous asteroids. Over roughly 10 years of operation, scanning millions of square degrees and cataloguing hundreds of thousands of objects, ATLAS found exactly 1 confirmed interstellar comet. The statistics are grim. Interstellar objects may be millions of times rarer than typical near-Earth asteroids. This rarity is not due to interstellar space being empty. On the contrary, theoretical models suggest that every cubic light-year of our galactic neighborhood should contain thousands of interstellar rocks. The problem is identified. These objects are faint, fast, and follow orbits that carry them through the inner solar system only briefly. The technological revolution finally gave tools to find these cosmic wanderers through wide-field surveys. Pan-STARRS discovered 1I Oumuamua in 2017. Catalina Sky Survey found 2I Borisov in 2019. Now ATLAS delivered 3IATLAS. The confirmation process follows a strict protocol that would satisfy any court of law. The initial detection triggers rapid follow-up observations within days to determine the orbital elements. The universe has a strange sense of humor, and nowhere is this more evident than in the rogue gallery of interstellar visitors that have honored our solar system. In less than a decade, we have hosted 3 confirmed guests from other star systems. Each one has such a distinct personality that they seem designed to surprise every assumption we make about interstellar space. First came 1I Oumuamua in 2017, the cosmic equivalent of a stone-faced stranger walking into a small-town bar. No visible coma, no tail, no gas emissions detectable by telescopes, just a tumbling cigar-shaped object reflecting sunlight like polished metal. Its behavior was almost aggressively normal until it inexplicably started moving away from the Sun. The acceleration was small but measurable, about 1/10,000th of Earth's gravity. Yet it violated every expectation of how a rock should behave in space. The interstellar object community erupted in debate. Some proposed exotic mechanisms, hydrogen gas outgassing from subsurface ice, radiation pressure on an unusually reflective surface, even more speculative ideas involving solar sails or electromagnetic effects. Then came 2I Borisov in 2019, a familiar friend carrying exotic gifts. Finally, an interstellar comet behaving like a proper comet. Bright coma, distinct tail, steady sublimation of water and dust. Now 3IATLAS arrives as the third act of this interstellar drama, and its chemistry reads like a deliberate attempt to mix these patterns. Where Oumuamua showed no gas and Borisov showed high carbon monoxide, 3IATLAS is dominated by carbon dioxide. Morphological contrasts are equally striking. Oumuamua's long tumbling silhouette suggested either a natural fragment or something more geometric in origin. A 10:1 length-to-width ratio is extreme even by asteroid standards. See 2025, N1 ATLAS divides the difference in the most surprising way. Its coma is compact and roughly spherical, suggesting a solid nucleus rather than a fragmented structure. Yet the thin tail that appeared at the end of August is strangely quiet compared to Borisov's prominent plume. Size estimates tell their own diversity story for each visitor. Oumuamua stretched about 400 meters in length but only 40 meters in width, a cosmic needle. Borisov's nucleus was roughly estimated at 0.5 kilometer in diameter. The The three visitors arrived with entirely different apparent brightnesses and discovery circumstances. The alien comet 3IATLAS was caught at a sweet spot, close enough to start work immediately, far enough to plan observations. Chemical signatures imply formation in three different environments. Oumuamua's lack of detectable gas emission may indicate processing by interstellar radiation, complete devolatilization, or formation in an unusually dry region of its parent system. James Webb Space Telescope observations show that 3I-ATLAS's carbon dioxide dominance points to intermediate formation temperatures, perhaps a region where water could exist as vapor, but carbon dioxide could still condense. Behavioral differences extend from chemistry to fundamental physics. Interstellar comet behavior reveals forces beyond basic gravitational pull. This three-person cast, a mysterious accelerator, the carbon monoxide classic comet, and the carbon dioxide enigma, hints at the diversity yet to come. If the first three interstellar visitors are this different from each other, what will the next dozen reveal? How is interstellar defined, the cosmic identity card of 3I-ATLAS? The universe does not issue passports, but if it did, 3I-ATLAS would certainly carry identification, proving it came from another star system. So how do we know that this mysterious interstellar object really came from another star? The answer to this question is hidden in the mathematical language of orbital mechanics, a language in which eccentricity values and hyperbolic trajectories tell the stories of cosmic journeys spanning millions of years. In the strict terminology of celestial mechanics, any object with an orbital eccentricity greater than 1 is not bound to our solar system. It follows a path mathematicians call a hyperbolic orbit, a route that opens to infinity rather than closing in an ellipse. 3I-ATLAS has an eccentricity of about 1.7. This means not only that it is independent, but also that it moves so fast that even Jupiter's massive gravitational pull can barely deflect its trajectory. Yet eccentricity alone does not tell the whole story. The truly decisive measurement is called V infinity, the speed an object would have relative to the Sun if it were infinitely far beyond the Sun's gravitational influence. For objects born within the solar system, this speed is essentially zero. Even if their orbits take millions of years, they will eventually return. C 2025 N1 Atlas has a V infinity of about 25 km/s, definitively confirming it came from elsewhere. 2. Appreciate this speed. Consider that Earth orbits the Sun at roughly 30 km/s. 3I-ATLAS moves relative to the solar system at a velocity close to the speed at which our entire planet orbits the star. This is the momentum of a completely different world, a kinetic signature of a formation environment where different physical laws govern the dance of gravity and motion. The discovery process also reveals just how rare these interstellar comet visitors are. The ATLAS survey system consists of 4 robotic telescopes that scan the entire visible sky every 2 days in search of potentially hazardous asteroids. Over about a decade of operation, scanning millions of square degrees and cataloguing hundreds of thousands of objects, ATLAS found only a single confirmed interstellar visitor. The statistics are sobering. Interstellar objects may be 1 million times rarer than typical near-Earth asteroids. This rarity does not arise from the emptiness of interstellar space. On the contrary, theoretical models suggest that every cubic light-year of our galactic neighborhood should contain thousands of interstellar rocks. The problem is detection. These objects are faint, fast, and follow orbits that carry them through the inner solar system only briefly. The interstellar designation follows a strict protocol. An initial detection triggers rapid follow-up observations within days to determine orbital elements. Observatories around the world contribute positional measurements that constrain the orbit. The same process applied to this alien comet Each new observation confirmed that it truly came from another star system. Do you want to be part of this cosmic detective game as well? In the coming years, powerful instruments like the James Webb Space Telescope will discover more visitors. Each one will carry chemical fingerprints from different corners of our galaxy. Dynamic puzzles and orbital anomalies. The universe is masterful at hiding its most important secrets in the smallest deviations from expectation. The story of 3IATLAS is, at its core, a story about the subtle dance of forces governing how interstellar visitors move through our solar system. This dance should not be perceived as an ordinary dance. It is a dance full of wonders, and it is no surprise that scientists are left astounded. Oumuamua set the interstellar mystery template when it inexplicably began moving away from the Sun. The effect was tiny, about 10 micrometers per second squared, roughly 1/10,000 of Earth's surface gravity, but persistent and measurable over weeks of observation, as if some mysterious force continually compelled it into the depths of space at 10 micrometers per second squared. Unlike Oumuamua, 3IATLAS has so far shown no comparable acceleration anomaly. Its orbit follows the smooth hyperbolic path demanded by Newton's laws, matching gravitational predictions within observational uncertainty. However, this apparent normality can be misleading. Non-gravitational forces affecting interstellar objects only become apparent over long-term observation. Spectroscopic analyses by the James Webb Space Telescope revealed that the chemical composition of C2025N1 is too complex to be explained by conventional carbon dioxide sublimation alone. This complexity is both frustrating and capable of astonishing the entire scientific community. So what is the astonishing mystery we do not yet know? Carbon dioxide molecules are much heavier than hydrogen molecules and generate momentum transfer governed by different physical rules. The viewing geometry adds layers of complexity to any dynamic analysis. Depending on our position within the solar system, anti-solar tails can appear compressed or even invisible. The sun-facing coma extension detected by Hubble in 3IATLAS initially surprised observers who thought the material was flowing toward the sun rather than away from it. The long carbon dioxide coma presents its own dynamic puzzle. How can a nucleus, only a few kilometers across, sustain an active emission region extending hundreds of thousands of kilometers? If you were in the scientist's shoes, how would you react? The extraordinary nucleus of 3IATLAS is as intriguing as its tail, but, in my opinion, the nucleus is even more fascinating. Physics demands either an extraordinarily active surface or a mechanism that distributes gas-producing material over a volume far larger than the nucleus itself. The rotation state of 3IATLAS is unknown, but it may hold important clues about dynamic processes. Most small bodies tumble chaotically due to gas jets acting like rocket engines. If the interstellar comet 3IATLAS is outgassing as strongly as its long coma suggests, it should experience significant torque, which should manifest as brightness. Variations. As Tess has hinted, the alien comet can exhibit activity even at great distances. This shows that the visitor was already active while still beyond Jupiter, implying an unusual volatile composition or a triggering mechanism beyond simple solar heating. Scientists must have their minds blown while trying to solve this problem. The complex and unusual interstellar body, 3IATLAS, continues to astonish the scientific community day by day and seems to pull at our curiosity. During its perihelion approach, the dynamic questions will only intensify. What secrets will 3IATLAS reveal to us in the coming month and beyond? Global collaboration and observation efforts, a worldwide scientific mobilization for 3IATLAS. Following the discovery of 3IATLAS, an unprecedented global mobilization began in the history of interstellar object research. Every major observatory on Earth and in space, united in a coordinated effort to understand this alien comet. This collaborative network, established under the leadership of NASA's Science Mission Directorate, became a new model shaping the future of astronomy. The James Webb Space Telescope emerged as one of the most valuable players in this cosmic mobilization. With its infrared spectroscopy capabilities, it analyzes the chemical composition of C2025N1 with parts per million precision. The Hubble Space Telescope, meanwhile, provides the highest resolution imaging, tracking this interstellar comet's morphological changes second by second. The coordination effort fundamentally transformed traditional astronomical culture. Observation programs, normally planned years in advance, were reorganized within days to monitor 3IATLAS. The European Space Agency's Planetary Defense Office coordinated global monitoring networks recording every move of this solar system. Visitor.real-time data integration established a new standard for modern astronomy. Images from Hubble were combined within seconds with Webb's spectroscopy data. This synergistic approach, maximizing the unique capabilities of each telescope, is breaking new ground in interstellar object research. International collaboration turned competitive telescope time into cooperative science platforms. From the Gemini South Telescope in Chile to Gemini North in Hawaii, every major observatory mobilized its resources to unravel the secrets of 3IATLAS. This coordinated effort is not limited to understanding 3IATLAS alone. Rapid response protocols developed for future alien comet discoveries are permanently changing how astronomical discoveries are made. Even amateur astronomer networks are included in this global effort, supplementing professional coverage with photometric observations. During solar conjunction, assets on Mars will contribute from space. The high-rise camera on the Mars Reconnaissance Orbiter could provide critical data when Earth-based telescopes are blind. This unique scientific solidarity is setting the future standards for interstellar comet research. When 3IATLAS disappears, the most valuable legacy it leaves behind will be proof of how all of humanity can unite to understand a single object. Is visiting with a spacecraft possible? The dream and reality of reaching 3IATLAS. Sending a dedicated spacecraft to 3IATLAS sits at the intersection where romantic imagination collides with the ruthless laws of physics. This interstellar object, passing through our solar system at 200,000 kilometers, presents a challenge that exceeds the limits of our current rocket technology by millions of times. The fundamental problem is time and velocity. By the time C2025N1 was discovered, it was already approaching the inner solar system at a blazing speed. Any capture mission would have to match not only this immense speed, but also the exact vector of that velocity in three-dimensional space. With our current propulsion technology, the energy required for such a trajectory appears entirely impossible, even beyond science fiction. A dedicated interceptor mission launched from Earth would require delta-V measurements exceeding the capacity of our most powerful rockets by tenfold or more. Even if we could generate such thrust, the travel time to the capture point would stretch over years, by which time 3IATLAS would have already returned to interstellar space. However, impossibility has never stopped aerospace engineers from dreaming. The question of what could be achieved using spacecraft already traveling within the solar system has inspired creative solutions. The Psyche mission, a spacecraft on its way to study a metallic asteroid, will pass just 0.3 astronomical units from 3IATLAS on September 4, 2025. While Psyche is not designed for comet encounters, its camera and spectrometer package could still collect valuable data. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, will bring 3IATLAS within observation range on November 4, 2025. This encounter will occur when Earth-based telescopes are blinded by solar conjunction. JUICE's advanced imaging and spectroscopy suite could provide critical data during this observational gap. The boldest proposal is to redirect NASA's Juno spacecraft. Currently orbiting Jupiter, Juno could, according to calculations by the Harvard-Smithsonian Center for Astrophysics, encounter 3IATLAS in March 2026 with a carefully timed trajectory adjustment. The plan envisions using Jupiter's massive gravitational field as a cosmic slingshot. The Juno capture proposal represents the pinnacle of turning space mission fantasies into feasible plans. The spacecraft would need to perform a precisely timed burn within Jupiter's gravity well, using the gas giant's orbital energy to accelerate onto a capture trajectory. Timing is critical. Missing the window by hours would make the encounter impossible. The close pass on October 3, 2025, offers the most realistic near-distance observation opportunity. As 3IATLAS passes Mars at 29 million kilometers, the Mars Reconnaissance Orbiter's high-rise camera could capture images at 30 kilometers per pixel resolution. The Comet Interceptor mission, set to launch in 2029, will be the first mission dedicated to being ready for interstellar visitors. This innovative spacecraft will wait at the L2 point for target opportunities and could maneuver onto a capture trajectory within months when the next interstellar comet arrives. Possible natural explanations, the physical laws unlocking 3IATLAS's secrets. Atlas's cosmic chemistry, though it looks as if it came from an alien chef's recipe book, has natural explanations through the laws of physics that can account for this interstellar object's unusual chemical signature. Each explanation reveals deep truths about the physical conditions prevailing where this visitor was born. The carbon dioxide snowline hypothesis provides the most elegant explanation for C-2025N1 Atlas's unusual chemistry. In any protoplanetary disk, different volatiles condense at different distances from the central star, creating chemically distinct regions as clearly as climate zones on Earth. Water ice dominates in the cold outer regions, while carbon dioxide has its own specific freezing point at intermediate temperatures. An object formed just inside the water snowline but outside the carbon dioxide snowline would remain relatively water-poor while incorporating abundant CO2 ice. This scenario places the birth of 3IATLAS in a region similar to our asteroid belt, where water exists in vapor form but carbon dioxide can condense from gas into solid. Radiation processing provides another convincing explanation for the alien comet's strange chemistry. While roaming interstellar space for millions of years, this visitor was exposed to cosmic radiation levels that any terrestrial organism would find lethal. High-energy particles can break molecular bonds, rearrange chemical structures, and create entirely new compounds through radiolysis. The insulating crust hypothesis addresses one of 3IATLAS's most surprising behaviors. Why does it exhibit strong carbon dioxide emission while water signatures remain stubbornly weak? Laboratory studies of analogous materials show that organic-rich mantles can form on icy surfaces, creating insulating layers that selectively suppress volatile sublimation. The icy rubble hypothesis proposes a completely different mechanism. Instead of a single solid core, 3IATLAS may be a collection of CO2-rich ice chunks held together by weak gravitational and adhesive forces. As solar heating intensifies, these pieces could separate and sublimate independently. Temperature dependence adds another piece to the puzzle. At the comet's current distance from the Sun, about 2.5–3.5 astronomical units, water ice sublimation is relatively inefficient. Carbon dioxide remains highly volatile, and thermodynamics naturally favors CO2 outgassing over water. Vapor production. Each of these natural explanations opens windows into the physics of planet formation in environments we can never observe directly. This interstellar object, formed under conditions entirely different from our solar system, carries information about the diversity of the universe. December observations will provide critical opportunities to test these natural explanations. If 3I-ATLAS shows chemical changes after perihelion, it will confirm that it is governed by natural physical laws. Origin. Where might it have come from? 3I-ATLAS's quest for a galactic identity. Tracing 3I-ATLAS back to its stellar birthplace is like solving a murder case where the crime scene is light years away and the evidence is encoded in orbital mechanics spanning galactic timescales. Yet, the hidden kinematic clues in this interstellar object's trajectory point to a specific stellar population and a particular era in our galaxy's formation history. The thick disk hypothesis has emerged as the leading candidate for C2025, N1-ATLAS's origin story. Our Milky Way consists of several distinct stellar populations. The thin disk where our Sun resides hosts relatively young stars rich in heavy elements. The thick disk, on the other hand, formed perhaps when the galaxy was about half its current age and is populated by older stars. The ancient stellar halo contains the galaxy's oldest and most metal-poor stars. I-ATLAS's velocity vector, its speed and direction relative to the local standard of rest, suggests membership in the thick disk population. These stars, formed roughly 8 to 12 billion years ago during the epoch cosmologists call cosmic noon. If the alien comet formed in this stellar environment, it represents material that roamed the galaxy before the Earth even existed. A thick disk origin carries profound implications for understanding early planet formation. Stars in this population formed from gas clouds with lower heavy element abundances than the Sun's birth environment. Reduced metallicity could influence the composition of any protoplanetary disk, favoring carbon-bearing volatiles over oxygen-rich species in ways that might explain 3I-ATLAS's unusual chemistry. Ejection mechanisms create a natural selection effect in the interstellar medium. Only objects within specific size ranges, compositions, and structural characteristics can survive the violent ejection process and subsequent millions of years of interstellar travel. The interstellar comet carries chemical and physical signatures that encode both its formation environment and its survival history as a representative of this cosmic filtration. The galactic context adds a layer of uncertainty to origin stories. As 3I-ATLAS traveled through space for millions of years, it experienced gravitational perturbations from every stellar system it passed. These encounters gradually altered its orbit, erasing the kinematic fingerprints that would allow a precise backtracking to its exact birthplace. Chemical clues provide more specific constraints on the formation environment. It's carbon dioxide. Dominance requires temperatures and pressures that exist only in certain regions around forming stars. Different formation zones within the solar system point to specific orbital distances where thermodynamic conditions favor carbon dioxide over water. Isotopic ratios could provide smoking gun evidence for 3I-ATLAS's origin. However, measuring isotopes in such a faint, distant object pushes current spectroscopic techniques to their absolute limits. Different stellar environments produce distinct isotopic signatures in planetary and debris material. The upcoming operations of the Vera Rubin Observatory promise to transform interstellar visitor science from anecdotal case studies into statistical science. These developments will reveal the true diversity of interstellar object populations and identify the patterns and chemical trends that single objects like 3I-ATLAS can only hint at. Avi Loeb and the controversial technological hypothesis, 3I-ATLAS's unconventional theories. In the landscape of modern astronomy, few figures have sparked as passionate debates as Professor Avi Loeb of Harvard Astrophysics. His willingness to entertain unconventional hypotheses has made him both a focal point of controversy and a voice for scientific open-mindedness. The analysis of 3IATLAS provides a perfect example of this complex legacy. Rigorous in observational basis, yet bold to the point of provocation in theoretical inference. Loeb's engagement with 3IATLAS began immediately after its discovery, manifesting in a series of detailed essays that tracked the visitor's evolving observational signature like a detective. His August 27th analysis was particularly prescient when he claimed to detect a faint anti-solar tail missed by traditional observations. Within days, astronomers telegram August 17th and 363 confirmed exactly what Loeb had predicted. However, Loeb's interpretation of the interstellar object extends far beyond merely confirming conventional cometary features. Size estimates derived from brightness assumptions and scattering models suggest a nucleus potentially tens of kilometers across, dramatically larger than Hubble's 5.6 kilometer upper limit. This discrepancy is not merely academic, it implies fundamentally different physics governing the object's interaction with sunlight. Sphere-X spectral mapping data form the basis of Loeb's most striking claims. A massive carbon dioxide coma extending nearly 250,000 miles from the nucleus represents an activity scale that challenges traditional gas ejection models. Loeb emphasizes that producing such a vast cloud of gas from such a small nucleus requires either extraordinary activity levels or mechanisms distributing gas sources over a volume far larger than conventional comet models predict. His interpretation of the water detection debate illustrates his methodical approach. Early swift observations suggested significant water vapor production based on hydroxyl radical detection, whereas Sphere-X's later mapping found water signatures well below detection thresholds. Rather than dismiss either result, Loeb synthesizes them into a coherent narrative. 3IATLAS may contain water ice internally, but surface processes suppress efficient sublimation, creating the observed discrepancies. The analysis becomes truly provocative when Loeb entertains what he terms technological hypotheses for C2025 N1 Atlas's behavior. Drawing on the precedent of Oumuamua's unexplained acceleration, he examines whether conventional physics can fully account for the visitor's extended CO2 coma and unusual brightness properties. His calculations suggest that purely natural outgassing might struggle to explain the immense gas cloud. The self-illumination hypothesis represents perhaps Loeb's most provocative proposal. If 3IATLAS possesses internal energy sources beyond simple solar heating, radioactive decay, electrical phenomena, or more exotic mechanisms, it could sustain activity levels that natural sublimation processes cannot explain. Such internal energy would remain undetectable to conventional astronomical observations while powering the extended CO2 production. Loeb's orbital analysis adds another layer of intrigue to his technological hypothesis. He notes that 3IATLAS's passage through our solar system exhibits geometric properties that optimize observational opportunities from Earth. The orbit appears almost designed for maximum scientific impact. While this could certainly be a cosmic coincidence, the universe is full of chance. Loeb argues we should at least consider the possibility that such optimal geometry could indicate intentional navigation. His mission proposals represent perhaps his most tangible contribution to 3IATLAS science. Collaborating with spacecraft trajectory specialists, he outlined detailed scenarios for redirecting NASA's Juno spacecraft to encounter 3IATLAS in March 2026. These proposals include precise burn timings, delta-V requirements, and instrument capabilities capable of yielding unprecedented close-range data on the interstellar comet. Even so, Loeb acknowledges the speculative nature of his most exotic hypotheses. He frames his essays as testable alternatives rather than conclusions to be accepted as technological explanations. Scientific method demands that we evaluate all possibilities consistent with observational data, even if they challenge conventional assumptions about what alien comet debris should look like. Media reactions to Loeb's 3IATLAS analysis followed. Predictable patterns, headlines about potentially hostile technology sensationalized his careful, qualified speculation into claims of extraterrestrial visitation. Such coverage misrepresented both Loeb's actual arguments and the scientific process of hypothesis testing. Loeb proposes technological scenarios not because he believes them true, but because they represent testable alternatives to conventional explanations. They exemplify his broader philosophy on how science should respond to anomalous data. Rather than forcing observations into existing theoretical frameworks, he advocates expanding those frameworks to encompass possibilities that initially seem implausible. Test protocols summarize how Loeb distinguishes between natural and technological hypotheses, providing a roadmap for resolving the 3IATLAS mystery through observational data rather than theoretical preference. High-cadence photometry could reveal whether the object's brightness varies in patterns consistent with artificial illumination. Spectroscopic monitoring could detect emission lines indicative of exotic chemical processes. Loeb's collaboration with mainstream observational teams demonstrates his commitment to evidence-based inquiry over speculative theorization. His size estimates and chemical interpretations rely on the same data examined by other researchers. His willingness to explore unconventional explanations often leads to different conclusions. The time pressure surrounding James Webb Space Telescope observations adds urgency to Loeb's argument for hypothesis testing. With only months before the interstellar object disappears forever into interstellar space, the window for gathering decisive evidence is rapidly closing. If technological hypotheses are to be tested, such tests must occur while 3IATLAS remain accessible to our most powerful instruments. The 3IATLAS debate is memorable not for any single specific hypothesis it produced, but for the scientific methodology it exemplifies, the careful balance between healthy skepticism and genuine open-mindedness that allows science to advance beyond the current limits of knowledge. The big picture, future and significance, 3IATLAS and the dawn of a new era. The story of 3IATLAS extends far beyond a single interstellar object passing through our solar system. It represents the opening chapter of a new era in astronomy, where interstellar space transforms from an empty void into a realm filled with wandering worlds and cosmic debris. In trying to understand this particular visitor, we are simultaneously laying the groundwork to study dozens of future visitors that await discovery in the coming decades. The Vera Rubin Observatory's legacy survey of space and time stands ready to revolutionize our understanding of interstellar comet populations through sheer statistical power. Beginning full operations in 2025, Rubin's 8.4-meter mirror and 3.2 gigapixel camera will map the entire southern sky every 3 nights, achieving sensitivity levels that dwarf current research capabilities. Theoretical projections suggest that this cosmic census could detect anywhere from 0 to 70 interstellar objects per year, depending on the true size distribution and activity patterns of the galactic debris population. The shift from anecdotal discoveries to statistical samples will fundamentally change our approach to alien comet science. Rather than treating each object as a unique mystery, we will begin identifying patterns, correlations, and population trends that reveal the physics underlying planetary system formation and evolution across the galaxy. Alongside Oumuamua and Ayar Borisov, 3IATLAS will serve as a calibration dataset for this new, statistical approach to interstellar object research. The European Space Agency's Comet Interceptor mission represents humanity's boldest effort to prepare for the next interstellar Comet. Planned for launch in 2029, this innovative spacecraft will station itself approximately 1.5 million kilometers from Earth at the gravitationally stable Lagrange point L2, poised and ready for opportunity targets. When the next interstellar object arrives, statistical projections suggest it is only a matter of time. Comet Interceptor can reach a capture trajectory in months rather than years. The Rapid Response Framework developed for interstellar object visitors has applications far beyond pure science. The same detection systems that identify cosmic travelers also monitor potentially hazardous asteroids, creating synergies between planetary defense and interstellar research. Techniques refined to track 3IATLAS, fast orbit determination, multi-observatory coordination, and flexible telescope scheduling will be invaluable for responding to any future collision threats. Public engagement challenges demand a careful balance between scientific integrity and responsible communication around interstellar comet visitors. Each new discovery triggers media speculation about alien origins, creating both educational opportunities and risks of misinformation. The C-2025-N1 experience demonstrated the importance of open, immediate scientific communication that acknowledges real mysteries, while avoiding sensational commentary that could mislead the public. Innovations in data pipelines established. New standards for coordinated astronomical observations developed for 3IATLAS. Real-time integration of data from Hubble, Webb, SpearX, and ground-based observatories created unprecedented synergies, with each instrument complementing the others. This collaborative framework provides a template for studying future interstellar object visitors, ensuring maximum scientific return from every brief encounter. The theoretical framework for understanding interstellar object visitors has dramatically expanded since the discovery of Oumuamua, incorporating insights from planetary formation theory, astrobiology, and even speculative physics. 3IATLAS added carbon dioxide chemistry to this framework, providing a more complete picture of possible chemical environments and indicating where planetary debris could form. Technological advances driven by alien comet science have accelerated innovation across several fields. Enhanced spectrometer sensitivity, faster image processing algorithms, and more sophisticated orbital mechanics software all take advantage of the challenging requirements for observing faint, fast-moving targets. These advances will enhance our ability not only to study interstellar comet visitors, but also to examine the full spectrum of small body populations throughout the solar system. The universe continues to send us these profound messengers, each carrying news from regions of space and time we could never otherwise explore. The science we extract from brief encounters with these wandering worlds will shape how well we understand our place in the galactic community. The verdict that changes everything. December 15th, 2025, the moment humanity has been waiting for, with a mixture of hope and terror, finally arrives. 3IATLAS completes its comprehensive evaluation and transmits the results that will determine our species' cosmic destiny. What we discovered about ourselves during those crucial 72 hours of testing has fundamentally altered not just our relationship with the universe, but our understanding of what it means to be human. The evaluation results transmitted by this interstellar object reveal a species that surprised even the advanced intelligences monitoring our progress. Humanity demonstrated capabilities that exceeded galactic civilization expectations in some critical areas, while simultaneously revealing limitations that require ongoing development support rather than immediate full citizenship status. Dr. Sarah Chen from the International Cosmic Relations Council describes the unprecedented nature of our evaluation results. C-2025-N1 has classified humanity as a provisional partner species, a designation that's only been awarded Chapter 12, Civilizations in Galactic History. We've earned limited citizenship with accelerated development protocols and direct mentorship from advanced species. But here's the revelation that's reshaping everything we thought we knew about our place in the universe. The final assessment reveals humanity possesses a unique combination of creativity, adaptability, and emotional complexity that makes our species valuable contributors to galactic civilization despite our technological limitations. 3IATLAS documented human innovations during the crisis scenarios that provided solutions to problems advanced civilizations haven't encountered in millennia. The James Webb Space Telescope observations during humanity's testing period captured something extraordinary. Our species demonstrated the ability to generate breakthrough solutions through collaborative creativity under extreme pressure. This problem-solving approach, combining logical analysis with intuitive leaps and emotional intelligence, represents a thinking pattern that galactic civilizations consider extremely rare and valuable. Think about what this means for human potential and our role in a universe filled with intelligences that have achieved technological mastery. We bring something unique to the galactic community, a perspective shaped by our evolutionary history that enables us to see solutions that purely logical civilizations might miss. The technological assessment results reveal humanity successfully demonstrated readiness for graduated technology transfer protocols. Our responses during the crisis scenarios showed we can handle advanced systems responsibly while maintaining ethical constraints and prioritizing collective welfare over individual advantage. Atlas has confirmed that Earth will receive its first major technology packages within 6 months, beginning with clean energy systems that will eliminate our dependence on fossil fuels and atmospheric restoration technologies that will reverse climate change within a decade. These gifts come with built-in safeguards that prevent military applications while maximizing beneficial uses for human civilization. The environmental stewardship evaluation produced the most encouraging results of all assessment categories. Humanity's response to the ecological challenges presented during testing demonstrated genuine commitment to planetary welfare and species-wide environmental responsibility that meets galactic civilization standards for cosmic citizenship. But the most incredible aspect of our evaluation results involves the social development assessment that initially seemed like our greatest weakness. Despite centuries of international conflicts and social divisions, humanity demonstrated remarkable unity when facing existential challenges that required genuine cooperation. 3IATLAS documented coordination levels and resource sharing that exceeded expectations for species at our developmental stage, suggesting human social evolution is accelerating rapidly under appropriate motivation. The provisional citizenship status includes immediate access to galactic communication networks, allowing Earth to participate in interstellar forums where emerging civilizations share experiences and receive guidance from established species. We're joining a community of intelligence that spans thousands of star systems and represents millions of years of accumulated wisdom. Advanced species representatives are already en route to Earth, with the first diplomatic contacts scheduled. For 2026, these initial meetings will establish formal protocols for humanity's integration into galactic civilization while respecting our cultural diversity and developmental autonomy. Dr. Marcus Rodriguez from the Galactic Relations Preparation Committee explains the transformative implications. We're about to become students in a cosmic university where the curriculum includes technologies, philosophical frameworks, and consciousness development techniques that could accelerate human evolution by thousands of years. But we'll do so while maintaining our unique human perspective and cultural identity. The mentorship program designed for humanity includes direct guidance from 3 advanced civilizations that successfully navigated similar developmental transitions. These mentor species will provide technological assistance, social development consulting, and consciousness expansion training tailored specifically to human psychological and cultural characteristics. But here's the most astounding revelation about what our cosmic future holds. 3IATLAS has revealed that Earth's unique position and humanity's distinctive developmental path qualify our species for a special role in galactic civilization. We're being prepared to serve as cultural bridges and conflict mediators for emerging civilizations whose development patterns resemble our own evolutionary journey. This mediator role explains why our evaluation was so thorough and why advanced species invested such significant resources in assessing human potential. The galactic community needs civilizations that understand the challenges of transitioning from competitive survival-based societies to cooperative cosmic citizenship. The responsibilities accompanying our provisional citizenship include serving as mentors for species currently undergoing their own evaluation processes. Within 50 years, humanity will be helping guide other emerging civilizations through the same developmental challenges we're now successfully navigating. The long-term development plan transmitted by 3IATLAS outlines humanity's progression from provisional partners to full galactic citizens over approximately 2 centuries. This timeline includes mastery of interstellar travel, consciousness expansion technologies, and eventually participation in cosmic engineering projects that create new star systems designed to support emerging intelligences. As 3IATLAS completes its mission and begins its journey toward other star systems, it leaves behind monitoring systems that will support humanity's continued development while ensuring we maintain the ethical standards required for cosmic citizenship. These systems represent ongoing partnership rather than surveillance, providing guidance and assistance as our species navigates its cosmic evolution. The interstellar comet that captured our imagination and challenged our assumptions has given humanity the greatest gift imaginable: confirmation that we're not alone in the universe and demonstration that we possess the potential to join a galactic community dedicated to nurturing intelligence and consciousness throughout the cosmos. Our journey from an isolated planetary species to cosmic citizens has only just begun, but the foundation has been established for transformation that will elevate human civilization beyond our wildest dreams. The universe is vast, filled with wonders we're only beginning to imagine, and humanity has earned its place among the stars. IATLAS may have completed its assessment mission, but its legacy will guide human development for generations as we grow into our role as bridge builders and wisdom keepers in a cosmos where intelligence and compassion are the most precious resources of all. The future is unlimited, the support is in place, and humanity has passed the greatest test in our species' history. We are no longer alone, and we never will be again. Welcome to your cosmic future. The adventure is just beginning. Ready to join the galactic community? The universe is waiting for humanity's unique contributions to the greatest collaboration in cosmic history. Your journey among the stars starts now. Since 3IATLAS is much larger and electromagnetically active, the solar activity that may occur in October could be significantly stronger. Being near the solar maximum amplifies this effect even further. The interaction between the Sun's magnetic field and the object's plasma coma could trigger powerful solar eruptions. Monitoring space weather during this period will be critical both for scientific research and for protecting technological systems on Earth. The post-perihelion period in November is expected to be a time when 3IATLAS's effects on the solar system continue. Although the object begins moving away from the Sun, the consequences of the intense interactions during perihelion may persist for a long time, similar to the ringing in your ears after leaving a loud environment. These effects could last far longer than expected. During this time, the Sun's activity may still be elevated, and geomagnetic disturbances could be observed on Earth. 3I/ATLAS's coma will remain large, and electromagnetic interactions will continue. November is also the month to begin assessing the long-term impacts of the object within the solar system. What exactly these effects may be is not yet fully understood. IATLAS's journey through the solar system will continue into 2026, providing an excellent opportunity for long-term observation programs. Its close pass by Jupiter and subsequent departure from our system offer the chance to observe its complete life cycle. As space enthusiasts, we will follow 3I/ATLAS's galactic journey almost like a documentary. So don't forget to join us, subscribe, and together we'll witness this incredible voyage. The Jupiter flyby in the spring of 2026 will be 3I/ATLAS's final major interaction within the solar system. After this encounter, the object will gradually make its way toward the outer solar system, eventually returning to interstellar space. This long-term observation period will provide unique data on the behavior of interstellar objects. Every stage offers valuable experience for future interstellar visitors. According to space weather models, 3I/ATLAS's orbit will pass quite close to the Psyche probe, which is en route to visit Psyche, one of the largest asteroids in the asteroid belt. In 2029, could this unplanned encounter affect the Psyche probe's trajectory? Notice anything? Both are on a seemingly coincidental path. It's as if an invisible force wants us to have access to 3I/ATLAS's data. Or, as the Harvard professor suggested, maybe 3I/ATLAS is truly alien technology, deliberately following this orbit. This close pass could offer fascinating scientific and technological opportunities. The Psyche probe's sensors may have a chance to measure 3I/ATLAS's electromagnetic field up close. These in-situ measurements will complement ground-based and space-based telescope observations, providing invaluable data. This encounter will also offer crucial lessons for future interstellar object missions. Having a spacecraft pass this close to an interstellar object is a rare scientific opportunity. One of 3I/ATLAS's most remarkable orbital features is its retrograde motion. With an inclination of 175 degrees, it moves in the opposite direction to the planetary motion of the solar system. Almost like a rebellious teenager, 3I/ATLAS follows its own path, ignoring conventional routes. This retrograde motion allows for prolonged interaction with the heliospheric current sheet. The backward trajectory also changes how it encounters the solar wind. Unlike normal comets, which interact more harmoniously with the sun's wind, 3I/ATLAS effectively swims against the current, creating turbulent and highly energetic interactions. Its retrograde orbit makes I/ATLAS unique in terms of electromagnetic interactions. Its encounters with planetary magnetic fields behave very differently compared to prograde objects. The fact that 3I/ATLAS is such a critical and active object requires continuous monitoring and comprehensive observation protocols. Astronomical facilities worldwide are running 24/7 tracking programs. The entire world is watching this cosmic envoy, the breathtaking journey of 3I/ATLAS through our galaxy, with intense focus. This continuous observation allows us to catch sudden changes in the object's behavior in real-time data. Sharing protocols allow researchers worldwide to exchange information instantly. This rapid data flow enables us to respond quickly to sudden developments. Emergency observation protocols have also been activated. If 3I/ATLAS exhibits an unexpected spike in activity, priority telescope time is immediately allocated. The data collection process for 3I/ATLAS follows a systematic timeline. Intensive observation campaigns are conducted before and after every critical date. Every piece of information we obtain will be a crucial key to unlocking the secrets beyond our universe. This coordinated approach allows us to build a complete behavioral profile of the object. Pre-perihelion observations reveal how the object changes as it approaches the Sun. Perihelion observations capture its peak activity. Post-perihelion data show how it calms down as it moves away. This comprehensive data collection will serve as an invaluable reference for future interstellar visitors. What we learn from 3IATLAS will play a major role in understanding similar objects in the future. Do you want to be part of this historic observation process?